explainability and bias in machine learning. So let's greet this awesome guy.
Awesome, awesome. So thank you very much for that great introduction. Are you able to hear me in the back? All good? Awesome, perfect. So thank you very much for the invitation. It's a pleasure to be here today at the PyCon Belarus. Today I'm going to be talking about a practical guide towards explainability and bias in machine learning. As it was mentioned, I am the chief scientist at the Institute for Ethical AI and Machine Learning, and I'm also a contributing researcher for several industry standards on algorithmic bias and risk assessments for industry AI deployments. And today what we're going to be covering is a hands-on example, a fictitious example with this company that we're going to call HypeML. And what we're going to be doing is we're going to perform the automation of a loan approval process. We're then going to discuss the terminology and why it's not just about removing bias. Then we're going to dive deep with this XAI library, which is a practical framework to mitigate, not fully remove bias. And then we're going to apply this framework to our example. So let's do this. We're going to be using this library called XAI, which the Institute maintains. It's available and you can check it out. Feel free to contribute with issues or pull requests. So let's take on this situation. HypeML suddenly gets a new project where business is super excited because an insurance company has requested to automate an internal process where they have a lot of domain experts reviewing loan applications and either approving them or rejecting them. They receive over 1 million applications over a year, so they want to automate the process. And business wants it right now or yesterday, if possible. They heard some competitors using this machine learning thing, so they definitely want to have that fully shiny thing in place. So the team, the HypeML company, had a look at what the machine learning standard workflow look like. And they realized that what it looks like is, getting some data, defining some features, selecting the model and the hyperparameters, and then with some scoring framework, scoring metrics, iterate until they're happy. Once they're happy with the performance of the model, they put it in production so that it performs inference on unseen data. And that's what they basically saw. So that's what they went to do. So they asked for data. Business came back with an Excel file with 25 rows. And they were like, we cannot do anything with this. So HypeML managed to convince them to get an Excel file with label data, historical data of 8,000 rows. So then it began, the journey towards greatness, the HypeML journey towards greatness. So we basically get this initial data set. And as we see, we have 13 features consisting on things such as age, working class, education, gender, ethnicity, and whether the loan was approved or rejected. We have 8,000 different examples with the 14 different features, including the label, the target label. And we perform the usual process. We split our data into train and validation. We have 6,000 on the training and then 1,600 on the validation. And then what we do is we just take a model, a single layer with 100 neurons, and we train it. The model has a softmax layer at the end, which means that the output is going to be a probability between 0 and 1. If it's over 0.5, then the loan is approved, otherwise rejected. Right, and we train this model. When we evaluate it, we see that we get 98.7% accuracy. So our initial accuracy was almost 99%. So what better result on a Friday evening? So let's ask over here, who thinks that it's a good accuracy and we should push it to production? Let's see a show of hands. Nice, nice, some cowboys in this room. Perfect. So we push to production, and then a few weeks go by, and suddenly BuzzFeed News pushes an article, HypeML deploys racist, sexist AI. And, the whole HypeML team is sitting there going, but we followed the instructions in the internet. How could this happen? And with this very, very simplified example, what they did is they went back and they diagnosed. So they asked business to gather the 110 examples that were processed in production and label them so that they can actually see what the performance of the model actually was. And when they actually received it, you know, as I mentioned, there's 110 examples with the 13 columns and then the label of whether it was approved or rejected. And when we actually evaluate our model, we see that we have a 54% accuracy on this data that we saw in production. And when we actually get a deeper insight into confusion matrix, where we see the number of expected approve and the predictive approve, we see that the model, what it was doing, it was just rejecting everything, right? It was getting an application, rejected, no matter what, just rejecting everything. And we can see this, that everything was going into rejected. And the team was sitting there like, why? Okay, let's actually see more metrics, like our ROC curve, which tells you whether your model performs better than randomness. And we can see that our model performs exactly like randomness. So we could have just deployed a function that returns random, and it would have performed probably around the same level. And when we actually visualize the data set in training and what we actually saw in production, we saw that the training data, we had a lot of examples for rejected, but very few for approved. And in the production data set, we actually have several that were supposed to be accepted, but they were all just rejected, right? And in this very simplified example, we've actually seen an overview of this topic of undesired bias and the need for explainability. And you know, this topic has become popular because of the high-profile incidents like Amazon's sexist recruitment tool, or Microsoft's racist chatbot, or negative discrimination in automated sentencing, and other cases where black box models that learn a lot of complex patterns, you know, that cannot be interpretable. And the thing that we have noticed is that organizations often don't go and are afraid to use these emerging technologies, not because of the risks, but because of the unknown risks. And the fact that they see these high-profile incidents happening in front of their eyes, thinking, oh my God, that's going to happen to me. So the reason why this is also very challenging is because you know, this problem needs people to see it beyond an algorithmic challenge, right? Large ethical considerations should not just fall on the shoulders of a single data scientist. And the way that we tend to explain why this is such a complex problem is because you have the technical area, this intersection of data scientists, software engineering, and DevOps engineering, creating this machine learning engineering field or role, which takes best practices from each of these fields. However, in practice, often you have data scientists that are deploying code into production, but perhaps are not following best practices from software engineering. Or vice versa, you have software engineers that build models and they don't actually use statistical metrics beyond accuracy, which are best practices within data science. And even if this is already hard enough, when we take this ambiguous field of machine learning engineering and we take it into industry, you find this intersection of machine learning engineering, industry domain expertise, and policymakers, right? And they're all trying to work together to come up with industry standards or means to be able to reduce risk and introduce accountability. And there's a lot of good work happening in this sort of areas, but it's in isolation. What needs to happen is to make sure that there is that cross collaboration between the technical sort of like intersections and the industry challenges that are being faced. And this is something that needs to go beyond industry. It needs to also be something that happens in research. There's a lot of research papers that try to tackle this issue of explainability and bias, but often it only has the technical insights and doesn't bring that domain expertise. So it's important to make sure that there is that perspective and that input from cross-functional sets of people. That's why at the Institute we work with ethicists, psychologists, etc., industry domain experts to be able to bring their best practices. And the answer is not just about removing bias, right? Because any non-trivial decision, i.e. that has more than one option, will have an inherent bias without exceptions. Unless you deploy a machine learning model whose only response is maybe, you will have an inherent bias within there, right? In machine learning, you're trying to discriminate towards the right answer. And the difference within your statistical error, that's already something that is considered as bias. When you go beyond statistical bias, when you talk about societal bias, that is challenging because societal bias itself is inherently biased. What that means is that something that someone may consider as racist or sexist, someone else in another location may not consider that is racist or sexist, right? So it is a challenging thing that is temporally based, and however, it still needs to be tackled. So let's see what undesired bias actually looks like. The way that we see it is in two sections. It's before the project begins and once the project starts and decisions are made. So before the project begins, these are errors in scope or bias a priori. These are suboptimal business objectives, lack of understanding of the project. This is incomplete resources such as not enough data or not enough time, incorrect labeled data. This could potentially be data that was labeled correctly for 20 years ago, but is no longer considered as labeled correctly. Lack of relevant skill sets within the teams, or societal shifts in perception, right? So this is once the project begins, what are already the constraints that make the project be biased from the ideal. And the second one is once the project begins, the bias a posteriori, every decision that is made throughout the delivery of the project, every decision made to choose a model, to choose the features, to choose the accuracy metrics, there is potential errors introduced within there that introduce that statistical divergence between the ideal that you could get and what you actually obtain. And it's also important to make sure we remember that explainability doesn't equal interpretability, right? You can have interpretability into a machine learning model, but that doesn't mean that you can explain the predictions. And that's why it's important to introduce this ability to remove or mitigate undesired bias through a combination of tools and process, right? And the way that we break it down is, is focusing on processes and best practices. Like in cybersecurity, it's impossible to avoid all hacking attacks, right? It's impossible. But by introducing best practices, you can mitigate at least a few by making sure that your infrastructure and your processes are in place. Similarly, it's impossible to just remove undesired bias completely, but it's possible to introduce a process that introduce accountability and mitigates basic divergences. Using the right tools with the right domain experts, there's a lot of numerous techniques that can be used in best practices within data science, but it's about sitting down with the experts that understand the field and would be able to tell you how a specific correlation or a specific feature importance really reflects in practice in that field, right? And ensuring that humans are leveraged, right? There can be a difference between deploying a model that is performing predictions by itself or introducing a human-in-the-loop review at the very end to make sure that the risks are reduced, right? And this depends on the risks within the process. And how it actually looks like, it's taking this existing data science process that is known by everyone or most people in this room, and introduce three key steps. The three steps are, number one, data analysis aligned with the business objectives. And this requires assessment of class imbalances, things like protected features, correlations within the data representability. The second one is on model analysis and model evaluation. So this is understanding feature importance, using model-specific explainability methods, using domain knowledge abstraction. What are the patterns that the model learned that then could actually be explained by a domain expert and perhaps be introduced as features a priori to the model, right? So you remove some of the complexity from the model itself. And the last one is production monitoring. And this is important because as soon as you put a model into production, it starts to deteriorate, right? Similar to a piece of technology that starts becoming more legacy. But in data science and especially in machine learning, when you put a model in production, you may actually see divergence due to the temporal nature of data. For example, if you have a financial data set, things like inflation may affect the model that was already trained, right? So it needs to, you need to make sure that you set the right metrics to monitor the models that you put in production in the short term and in the long term. And what this looks like into our model is basically you get your data and then you perform data analysis with the right tools and the right domain experts. When you train your model, you assess and evaluate the performance of the model as well as metrics, and we're going to see how that looks like. And then you set the metrics to then be able to monitor within production, right? This requires maturity in the infrastructure in order for you to be able to do that. And this is why it's important to understand that there's an explainability trade-off. And introducing fail-safe mechanisms, removing features or introducing simpler models can have an impact on accuracy, right? And not all use cases demand the same level of scrutiny, right? Like building a prototype may not require the same level of processes introduced than automating a recruitment process at scale with hundreds of thousands of people interacting with it, right? And the ones that are more critical require more scrutiny, more explainability, more interpretability. And similar to enterprise software, yes, it introduces a level of red tape that may slow down development, but when you develop enterprise-ready systems, they require much more a heavier infrastructure around the systems themselves. So it's not just the piece of technology, it's everything that comes around it. And there's many tools available for this. There's XAI, which is the one I mentioned. There's also SHAP, Lime, ELI5. And we actually created a list called the Awesome Machine Learning Operations list that you can check online. Which has not only explainability and for prediction and models, but also things like privacy preserving machine learning, etc. One of the things that I forgot to mention actually is that the link is on the corner of the slides. If you access it, you can get access to all the links. And so let's jump into it. Let's go back into our example and see how these 3 steps actually look like. And let's start with data analysis. So with data analysis, what we're going to do is we're going to first import the XAI library. And what we will manage to do now is we're going to take the initial data set and see what we have, which is a similar one. We're going to then be able to use this library to understand and analyze the data sets. In this case, we want to analyze how the data set breaks down in the gender feature, right? And what we can see is that we can visualize some of the imbalances, the number of examples that we have for each of the genders within the data set. So here we can see that we have over double of examples on male than with female. The second one, is when we visualize as a breakdown, is that even though we now have more examples, when we break it down by our target feature alone, we can see that the number of examples for approved female are very, very few, right? So even though it actually looked like it was slightly more balanced, we would still, if trained the model with this data set, the model would still be trained with those imbalances. And again, remember, it's not about making sure everything is completely balanced. It's about being conscious of what are the initial imbalances that your data set has and having the right people with the right skill sets to make sure that they can have their say on whether this is a representative data set for what will be seen in production. What we can do now with this library, you actually can use upsampling and downsampling to balance a data set. So what we're basically doing here is we're saying that for the gender with a cross of the target function loan, we want to upsample all of the data points that are less than 0.5 up to 50%, right? And we want to downsample all of the ones. We can, for example, remove the downsampling, and we can see that the ones for male rejected, are still higher. So it just allows you to play around with some of the features by using upsampling and downsampling. What you can do as well is you can define what are your protected features, things that perhaps you wouldn't use to training your model, but still would like to understand breakdowns of the data set that you have. And in this case, we're seeing the imbalances within ethnicity. We can see that we have more examples for one class than the other. For age, we have less examples for people over than 60, etc., etc. And then we can also visualize the correlations. So here we're actually visualizing the correlations in a dendrogram. We can see things like, native country and ethnicity are quite correlated, or marital status and relationship. With this perspective, we know that if we remove one of those and we still keep the other one, the model will still be able to infer some of those patterns when seeing the inference. Again, it's not about just removing everything from the model. It's about being conscious and being able to monitor in production when you have this, potential high-profile screw-ups. And then you can also visualize it on a matrix perspective. This is just your usual correlations matrix. What we're going to do now is be able to do a balanced cross test train split, right? So when you actually split your data set, one of the most important things is to create your validation data set, the data set that you're going to use to quantify the performance of the model. And for this perspective, you would want to make sure that it's as close as possible to what you will see in production. Again, this is not to be the superhero and state what society should look like, but this is to be able to make those decisions, not just with one data scientist, but with the right domain experts. Now we jump into the next part, which is model analysis, model evaluation. And what we can do here, we're going to start by training our data set with training our model, the same sort of like structure with the data set that we have. We can see that here it doesn't just jump into high accuracy very, very fast, because it's probably not just learning to reject everything, which is, sometimes a good thing. And what we're going to do now is we're going to visualize how this new model performs. And we can see that now at least it has a much more reasonable balance when it comes to approved or rejected loans. It's not just rejecting everything, it's getting a few more accurate when comparing it with our sample validation set. When we visualize the ROC curve, we can see that it performs significantly better than randomness, which is always a good thing. And what is interesting is that this library allows you to visualize things like your ROC curves on a feature-specific basis. So what we're going to do here is we're going to visualize and create an ROC curve for each of the genders and see how that actually performs. So in this case, we can see that the ROC curve for male versus female, perhaps in some other sample, could be heavily, there could be a heavy disparity, right? So it's just to be conscious of the performance of the model itself. Other thing that we can do is actually run an understanding of metrics. So in this case, we're visualizing the precision, recall, specificity, and accuracy of the model. But what we can do is actually see the things like precision and recall for the feature itself. So you can actually see how the precision, recall, specificity, etc. performs for each of the genders. And this, again, is to make sure that you're conscious of potential divergences within the trained model itself, right? It's not about making sure that it's exact, because what does that even mean, right? But it's about making sure that now you can have those conversations with the right domain experts. Normally, it's not going to be as simple as just an obvious, sort of like protected features that just screams, gender. With the case with Amazon, what happened is that the model learned to use the gaps between employment to automatically reject potential candidates. And what that meant is that women that had maternity leave were automatically rejected, right? So it's then understanding how those biases get introduced and being able to mitigate it before TechCrunch, gets you a headline saying that you made it on purpose and you're the evil genius that, deploys racist models. What we can do as well is we can actually do feature importance, doing feature permutations. These are just techniques that we compiled into this one library, but it's everything about being able to have the right tools to sit down with the right stakeholders. In this case, we can actually visualize that things like capital gain, marital status have the biggest importance when it comes to performing inference into our model. And we can also see that our protected features, gender, ethnicity, are not as strong in terms of importance as others are. And what we can do as well is we can use other libraries like SHAP. SHAP is basically using shapely values that allow you to take for one specific prediction how each of the features affects that sort of probability at the end. So in this case, the probability that we got was around 0.17. And we can see that the fact that it's education number 13, it pushed it up by that much, right? And marital status, never married, pushed it down about that much, right? So we can see the importance for each of the predictions. And again, this is about sitting down and being able to use this information to make sure that your entire process is more robust. So it's a combination of interpretability methods for machine learning, but also is using that domain expertise. We can also use LIME, which is another technique similar to SHAP. SHAP is an improved sort of version. LIME uses local approximations, which is quite an interesting area. And you can still very similarly see how each of the features affects for that specific inference that we performed. And then for the last piece, production monitoring. So this is about setting metrics for you to be able to ensure that the models that you put in production perform as expected. And you can actually set metrics that you can test on a short period of time versus a longer period of time. Some of these tech companies, if they had actually set some metrics up front, of course, it introduces more red tape and it slows down potential deployment of the systems, but it avoids those high-profile scandals by making sure somebody checks within a specific period of time or you get notified. In this case, what we created is this visualization that we called the smile graph, which what basically it shows is the number of predictions that fall into the probabilities, right? So here is all of the predictions that fall in a probability bucket of 0 to 0.1, 0.2, etc., etc. What that means is that if it's over 0.5, it's going to be an approved loan, and it's either correct or incorrect. If it's lower, then again, it's going to be rejected, and it's either correct or incorrect. So that's what you're seeing here. And you can actually see it into more detail by showing the display breakdown. So basically is the true positives, true negatives, false positives, false negatives, seeing where your probability lies. And the interesting thing about this curve, and the reason why we show it, is because it allows you to ask questions such as, how would my model perform if we introduce manual review process upon a specific certainty when the model actually provides, say, for example, 70% certainty that the loan should be approved. You can see that all of the green stuff is what would be processed through a manual review. Right? So what you're saying is that humans would look at anything that goes within these areas. Of course, it's not just about just pushing this, because it still needs to answer the question of, well, what does it mean to have 0.7 or 70% probability, right? You have to understand what that really means on your specific use case. And with that said, revisiting our workflow, we can see that these 3 steps allow us to not remove bias, but actually introduce the right steps with the right stakeholders to have those conversations to understand what are the potential risks. And this is something that we're abstracting into what is now becoming industry standards, like the ISO 20XXX, that allows you to actually certify yourself that not you're completely never going to be having biases, but instead is that you have the processes to mitigate them. And with that said, this was an overview of explainability bias evaluation from a practical perspective with an example on a loan approval process. Again, the code, you can find it on bit.ly/PyConXAI. And thank you very much, and happy to take questions now or later at the pub.
Thank you. Let's start with questions.
Awesome.
Can you return to the slide where you have dendrogram of features?
Yes, I'll just change it to the Jupyter. Yep.
So, yes, there is features gender, and it's highly correlated with hours per week. It's, as I understand, it's how many hours per week person work, yes?
Oh, yeah, yes.
So it means that if we decide don't be sexist and say that we do not have gender features at all, our model will get who men and who women just based on hours per week. So
That is correct.
We have BuzzFeed news that said we are sexist anyway.
Well, so that's a very good question. No, it's a very, very good question. So again, I think it's worth emphasizing that the purpose is not to say you have to remove any sort of preconception on any protected feature, because that is always going to be impossible. There's always features that are going to be at least slightly dependent. And one of the main things to mention as well is that this data set is from the 1970s. It was just taken for this. But specifically to your question, it's really good point. The main perspective is not that it should be removed, but the decision shouldn't just be left to the data scientist to say, I'm going to remove it or I'm going to leave it. It should be a decision for the process from end to end based on how the current humans process it, right? So in a recruitment process that has no AI at this point in time may not allow the person to understand to use things like gender to base their opinion. However, that doesn't mean that companies don't still do their best to try to identify things that allow them to maximize for the candidates. Ultimately, it's never going to be possible to remove all that, but it's about making sure that the right people make the decisions of what needs to be removed and to what extent, and what to monitor to avoid potential discriminations. Again, there's the perspective of, well, if I train the model, should it positively discriminate? And that's another really hard question. That's something that is not just be taken lightly and a software engineer just changes the weights of the model. It's something that needs to be consciously done throughout the actual end-to-end process. But that's a very good point. It's domain specific.
It's going to be a bit of a long question, so apologies in advance. But
awesome, no worries.
So I've seen commonly both in the academic environment and in industrial environment and policy making that bias and discrimination and fairness in machine learning is often discussed in terms of model predictions, but an AI system typically does not end with model predictions. So like modeled predictions affect decision making, and decision making affects the underlying population. And it's quite common for the model to actually change its data under its own feet over time. And there was a very interesting published paper that got the best paper award at the latest ICML. It was about a situation where the group of researchers tried to not only focus on model predictions, but actually monitor a particular metric over time, like to measure the temporal effect of deploying a model into production. And they found a very interesting case on American FICO dataset credit scoring, that enforcing any kind of fairness constraints actually actively harmed both the institution and the demographic group it aimed to protect. So it sometimes can happen that like common sense tells us to have maybe like equal opportunity or demographic parity across some of the sensitive features, but in the end, shouldn't the result of a fairness framework be to not harm everyone? So I was wondering if you have any thoughts on like whether the policy making around this should change and how to adopt the ethical framework to go from just point predictions to actually the temporal effect over a long period of time.
Yes, that's a very, very good question, and I think that is one of the biggest issues that we're trying to portray here, is that bias is not really just an algorithmic problem, and it's not just something that can be tackled by removing features and just modifying, especially not just modifying weights. It's something that needs to be tackled throughout the end-to-end process that not just involves the deployment, but also the temporal nature of that process itself. And that's why when proposing this sort of like data science extension, it involves not just the perspective of data analysis and model evaluation, but also setting the metrics both in short and long term to monitor not just divergences of like statistical metrics of the model, but also potential reinforcement of the discrimination within the industry itself. Because sometimes you see that the deployment of a model could have a negative effect on the already disjoint or imbalanced crowd in which it's being used. So I think it's just the perspective of how can we make sure that we tackle this, not by just introducing tools, but by making sure that the right policymakers, right regulators are at each point in time. And also one of the other questions that needs to be introduced is in what extent policy stops and standards begin, and then at what point standards finish and best practices in software engineering and data science begin, right? Because then you need to be able to use basic terms within the legal sphere, like things like negligence, right? To be able to say, well, what is the level of accountability of, for example, why did something go wrong, right? How do you pinpoint that to? So that's a very, very good point, is how do you convert this into not an algorithmic problem, but a human, a long-term sort of problem.
We have time for one more question.
I have one question. Hi, Alejandro. Cheers for this talk. In the beginning, you've mentioned a really interesting question. You said that sometimes we have a problem when software engineers developing the machine learning models and when data scientists pushing it to production, right?
Mm-hmm.
It's a really interesting question. At the same time, in introduction, you said that you have a great experience in creating from scratch data science teams, right?
Yep.
So let's say this virtual bank from the beginning of your talk came up to you as a consultant and you've got a budget for 10 people. How would you split these 10 people between data scientists, software engineers, and DevOps? Do you have an answer for that?
Wow. No, that's a very, very good question. That's a very good question. So, unfortunately, there is no, like specific percentage, because that depends on the nature of the project. If it's B2B, you need more people in the professional services, sort of like integration, data engineering. If it's more like in-house B2C, you may need more people to focus on the infrastructure, like cloud sort of DevOps. So it would be different. But something that I've actually been seeing that is quite interesting is that there needs to be more focus than there currently is on the roles that require infrastructure. When it comes to data engineering, especially, that is a field that is already quite misunderstood, right? You can see it in, like, if you see a job application for a machine learning engineer or a data engineer, they're trying to hire somebody with data science skills, software engineering skills, perfect consultant skills for the salary of an intern, right? So, which is completely impossible. This is something that is already opening up to the problem, which is you can't just hire a superhero, a unicorn, to just do everything, right? It's how can you make sure that you have the right people at the right time? The one thing that you're correct is that you do need this combination of skills. So you will need data engineers, DevOps, software engineers, or full stacks. The ratio will depend on the nature of the project, but I think it's just coming into the realization that we need it. And that's why, one of the core things that I do mention and that I encourage is this machine learning operations sort of set of libraries. These are things that go beyond just the TensorFlow, right? It's things that you can use to orchestrate models, to do automated feature engineering, automated neural search, or, visualization to explain things. So it's things that are required based on the job. But I think the one answer that I can just say is that you will need all of those skill sets.
Cheers. Thanks.
Yeah, but really good question.
But okay, the last one, if I have one last second. Would you hire a data scientist who turned into data science after being software engineer?
Yeah, of course. I think it's similarly like there's people that come from one field and become in the other. I think it's just on defining what are the requirements for these roles, and I think that is what is the tougher thing to say is what do you need in order for that transition to be taken in a reasonable way.
Thank you.
Okay, let's thank Alejandro.
Awesome. Thank you very much, guys. Thank you.
So it was a great talk, and we will have like 2 minutes technical to meet our next speaker. Please do not